Okay, this is a quick video about Coulomb's law and Cartesian coordinates, and I want to underline coordinates there because we're going to set up a formal coordinate system with an origin to show how doing these kinds of problems can be easier in some circumstances. So here's a typical problem. Find the electric field from a dipole, a distance x to the left and y above. I have another video about dipoles where I dig in. I'm just using it here as an example. We're not really interested in dipoles for dipoles. It's just an example case. So let's draw our dipole. This says that we are interested in the field, a distance x to the left and y above. That's at that point P up there. Typically, the way you would learn how to solve these in most introductory books, and a way I teach too, because I think it's great, is you use Coulomb's law in spherical coordinates, which is what that guy is. You draw a bunch of vectors, you do a bunch of geometry, you find some angles, you find different radius vectors, and then you find components, Cartesian components from those spherical coordinates. That's a perfectly good way to do it. There are good things here, like you look at the length of each arrow, so you get some intuitive sense of how big the electric field is. But that's not what I want to do here. I want to just show you a way that requires less geometry. Okay. And so, what are we going to do? We're going to rewrite Coulomb's law a little bit differently. This r hat is kind of annoying and difficult to work with. So instead, I'm actually going to write this vector, r vector, because it's based purely on the coordinates. So there's that word, coordinates of things. So in other words, I need to first come up with an origin. Once you have an origin, you can then label each point you're interested in, the point of the charge, the field point you're interested in, by its coordinates. And then you can get rid of everything else. You don't need it anymore. The important thing now is that we find these vectors, r1 and r2. And those are easy to find since you have the coordinates. R1 vector is just the field point minus the charge point. So you do that for the x and you do that for the y in both cases. Once you have those, it is plug and chug. There's no geometry to do. You can clean it up a little bit and then simply write down that the total field is the sum of the individual fields. And look what I've done. I took my vector r and I just put it there. Down here, it's just the magnitude of r. There's really nothing else to do there. Same thing for this guy. I write the actual r vector, which I have, and then beneath it, it's the magnitude of that r vector. So there's less sort of puzzling here, so long as you take the time to set up a coordinate system from the beginning. Okay, the real advantage of this technique, I think, plays out when you have continuous distribution. So for example, here's a line charge. And I'm going to show you we're going to do the exact same technique, and there's less fussing and fiddling involved. So we make coordinates. Now in this case, the bar itself doesn't have a coordinate, and so I label the boundaries. The left end of the bar has this coordinate. The right end of the bar has this coordinate. My field has this coordinate. Once you make the coordinates, you can get rid of all the other nonsense in the problem, clean it up. And now the thing is, in order to make an r vector, I need to pick some place to make the r vector from. And so for continuous distributions, you know the trick is you pick some small slice of the distribution and just pretend that a small amount of charge, dq, lives in that slice. And let's see what the r vector looks like for that slice. That slice is located at L0. You might say, what's L? Well, L is somewhere between 0 and D. We'll figure that out later. Let's draw our R vector. Okay, so that's our R vector. And now since I have coordinates for my point charge and coordinates for the field point, it's really pretty easy to just go ahead and write down what that R vector is. And now, since I know what the R vector is, I can write down the electric field due to that particular small amount of charge. And so now you say, well, okay, that's just that bit of charge. How do you get the field from the whole bar? Well, you just do the same thing for every other little small bit of charge in the bar. And of course, there's an infinite number of those. And you're here, you're already looking at this video, you're smart people, you know that that means we're going to end up doing an integral. What does the integral go? It goes from the left coordinate of the bar to the right coordinate of the bar. Okay, our charge is the charge per unit length times some small bit of length I use there. Notice I use dl, not dx or dx prime or any of that stuff. It's just a dummy variable. In fact, I've already reserved the variable x to talk about the location I'm interested in the field. So I just need some letter or name for distance along the rod, and you can call that whatever you want. I happen to call it L. In this case, I just plug in what I had over here, and then the rest of the problem is some integral that I don't really care to do. What I will say, though, is you might say, this is weird. You have the integral of a vector. But you know that when you integrate a vector, it's the same as integrating each component of the vector. And so you see that by doing it this way, you don't have to come up with two integrals. You kind of are given two integrals just by virtue of the fact that you're dealing with the vector the entire time. What's the next upgrade from something like this? Well, of course, we go from 1D to 2D. You go to a 2D plane with a charge distribution sigma. And what are we supposed to do? We come up with coordinates for the boundaries. In this case, I have corners. So here's this corner, this corner, this corner, this corner. I also came up with a coordinate for the center because in this case, I changed my problem to say a distance x to the left and y above the center. Okay, once you have this, you can get rid of all the other garbage that we've been getting rid of at the same time. What I want to convince you here is that it's not more complicated to do a 2D or 3D object. It's just kind of more of the same. So what I have to do is pick a small piece of charge. That way I have a specific location that I can go from. I make an R vector just like I did in the last case. Because I know the coordinate of my charge and the coordinate of the field point, I can go ahead and write down the R vector. And then it's the same thing as I did before. I can find the electric field due to that R vector, just plugging and chugging into Coulomb's law. And then, okay, we're going to have to do some sort of integral here. That's fine. I integrate from one boundary to from one boundary to another boundary. That's along the L direction. And I go from minus d over 2 to d over 2. So I go from boundary to boundary is the point. And here I just have this double integral set up over here. I'm not telling you how to do this integral. I'm not saying it's even a nice integral to do. I'm just saying go put it in a computer. Let a computer figure it out. That's not your job. You have better things to do with your time. What you want to do is learn conceptually what the process of using Coulomb's law to find the total electric field due to a distribution. And one way you can do it is with spherical coordinates and angles and stuff. But if you're willing to write down coordinates, writing down vectors is a pretty easy extension of that. You might say, well, what happens if I have something that, I don't know, is round? Yeah, I agree 100%. When you have things that are round, maybe you do want to use polar or spherical coordinates or something like that, but you can still keep with Cartesian the whole time. Now, I'll tell you something about this is whenever you have a disk and you try and find the electric field off axis, you're not going to be able to do the integral in any coordinate system you pick anyway, which is why when you see in introductory textbooks, they always tell you to find the electric field on axis. That's not really my concern in this video. I just don't want you being confused by, well, how do you do that? You don't is the answer. You make approximations. But what I wanted to stress was it's quite easy to write down an R vector if you've made coordinates. If you haven't made coordinates, it can be a real pain in the butt. Okay, hopefully this video was more helpful than confusing.